Hello and welcome to Microfile, the best of the recent series of Microlive.
This week it's robots working in industry and playing in the more adventuresome world of the research labs. Here we've got a small industrial robot. So let's see what it can do. Put it through its paces. It's got, in fact, 6 joints. They're called the waist here. Then there's the shoulder, the elbow, the wrist, which is actually quite complex. It can do 3 different actions: roll, pitch and yaw, they're called. And it's even got a hand, there it is, which can clap. Now, each of those actions is driven by its own motor and controlled by its own microprocessor. Well, we've also programmed it to perform a typical sort of task which a robot like this might be used to do in industry. Here it's simply picking up objects from a very precise position and moving them to another very precise position. Now, the movements may look very simple, but in fact they're actually quite subtle. It's picking up those blocks very slowly, gently, then it accelerates and decelerates, and again puts them down gently. No prizes for guessing what it's building. It uses those 6 motors in a very precise combination, and it's that precision, and of course all the electronics, that make it so costly. This one in fact would set you back £30,000. Now, the main problem with this kind of setup is it can't deal with uncertainty. For example, if I took one of these blocks away, like so, the robot still thinks it's there and it will blindly go on through its actions. And of course, from here on in, we're right up the creek, dropping blocks all over the place. Now, you might think that adding a vision system would solve that problem, but in fact, interpreting images is very complex. Mike Brady, you're a robotics scientist. What's the problem about recognizing a simple object like a brick?
Well, there's no real problem for us in recognizing simple objects like this. After all, we know all about cubes. We can determine their color. And even if we were to place an object like this in a cluttered background, we'd still be able to distinguish it on the basis of color, on the fact that we can separate objects in depth and so forth. The problem is that robots don't really have the ability yet to make much sense of color, nor can they do very much with regard to depth. So they end up by taking a black and white image like you see on the screen.
And then it's very difficult to find our brick, let alone recognize which one we're after. What's the solution to that?
Well, as so often is the case in engineering, you solve the problem by essentially avoiding it. You try to separate out objects and you place them on a separate high-contrast background where the robot can move and pick them up.
Right, now that may seem to be ducking the issue, but in fact that's the approach we saw on Microlive a few years ago when we launched a competition to devise a ping-pong playing robot. And as you can see, in the Microlive studio, they still had a long way to go.
If I count down 3, 2, 1, go.
Oh, what? It tipped it.
Very
it tipped
nearly,
it.
very
8 out of 10
nearly.
for the smash, but how did it see the ball coming?
It didn't see the ball coming. This one, we cheated a little. We used a bit of guesswork on where the ball would arrive.
Right.
But it has got a vision system.
And come the day, those two will be joined together, the vision system and the action.
They've got to be.
What a fraud. But at Bell Labs in the United States, they took up John Billingsley's challenge, and this is what they produced. Now, Mike, avoiding all the mathematics of the ballistics here, how is the robot detecting where the ball is?
Well, rather like in the case of putting our block on the light table, we've set the table tennis ball up against the black background of the person wearing the black muslin shirt. We've simplified the table tennis table. We've got a TV camera above the table and one behind the bat. And so it can track the ball in those 2 cameras from binary images, and then with very simple trigonometry and arithmetic, rather like triangulating for a position of a yacht, it can find the position of the ball in space.
Right, well, it seems to work in the laboratory, and in real factories too. Vision systems depend on having a relatively easy feature to search for, a bit like that white ping-pong ball against black. Here, Fref reports from America on one advanced industrial application.
Two men install a car windscreen. Almost without thinking about it, they're communicating, taking cues from each other and from the production line as it stops and starts. They're governed by the speed of the line, which gives them only a small window of opportunity to press home the glass. They do this with human skills, which we take totally for granted. Recently, at the General Motors Buick City plant near Detroit, they've automated this skilled but tedious part of the car production process. Here, instead of men, robots cooperate with each other in what's known as a flexible work cell. On the left, a group of 4 robots prepare windscreens for a range of cars of different shapes, sizes, and colors. On the right, a vision system looks at each car as it comes along the production line and tells one of the robots exactly where to place the windscreen, a slightly different position for every car. And round the back, a similar group of machines puts in the rear windows. But the system isn't yet smart enough to load the right windscreens in the right order for the cars as they arrive. A carousel still needs a man to load it. This takes the windscreen to 3 robots in turn, which prepare its edge with the chemicals which will glue it to the car. If the glass weren't held firmly in the right position, these robots wouldn't have any idea where it was. They're blind. But no human would spray so evenly, or so quickly, or so tirelessly throughout the day. Each robot has its own computerized control system to guide its complex movements in space, and a different program for each size of windscreen. So how do the men and the machines know in what order cars are coming along the production line? Every car on the assembly line has one of these attached beneath it. It's a short-range microwave transmitter programmed with a numeric code which identifies what kind of car it's supposed to be when it comes out the other end of the plant. This one might say, "Hi, I'd like to be a red Buick LeSabre 2-door with black seats, a thermal rear window, and the following options." As a car moves down the assembly line, receivers in the floor pick up this number, and the men and the machines in each workstation act accordingly. A massive cabling carries messages between the machines. It tells them when to start or stop, which program to run, and brings the latest news from the various sensors. Software was developed here specially for this work cell. The most difficult thing was tying in the vision system. That's the unique feature. Using a number of black and white cameras, each car is viewed from a number of angles under very bright and very even illumination.
The vision has to be within 3 to 4 millimeters accuracy when they load the windshield in the car. It's looking for the contrast and the edge around the windshield opening. It focuses in on that point, and there are 4 different cameras that look at that point, giving us a 3-dimensional picture of the car edge.
What you're seeing here in real time are the lines of high contrast that the computer has picked out from each black and white image. From this massive information, it has to identify the edges and angle of the window opening in each view, then use a bit of 3-dimensional trigonometry to tell the robot precisely where to move.
Now, with the ping pong ball, Mike, you're looking for a single point in space. That looks to me to be much more complex, is it?
Not particularly. After all, General Motors went to a great deal of effort to simplify the contrast colour of the car, the lighting. They had 2 or 3 cameras sprinkled about. They were looking for a very simple feature, and again, to triangulate, to find that windscreen opening in space, much like the ping pong ball. In both cases, they needed vast amounts of computing.
Right. Let's move back to our problem here with the block amidst all the clutter. Here is a remarkable piece of film which shows a computer solving that problem.
Well, here you can see an example of a bin full of castings with one stray object which has to be removed because the computer only knows about one kind of object. Central to the operation of the program is that the computer has a model inside its memory of that casting. In this case, it looks like a computer-aided design model. The robot uses a laser ranging system to compute explicit depths, so solving the tough vision problem we saw earlier. Here the edges are depth edges where the surface intersections on the objects.
It's only got the one eye, has it?
It's only got the one eye, but it's computing depth. Now what it's doing is finding little edges and trying to match them up against its model that's stored in its memory. And every time it finds one, it makes a hunch about where a model is in the memory of the computer.
So then it tests that hunch against other things. It predicts that there must be another edge over there and then tries to fill it in.
That's right. And the more information it finds, the more it can narrow its hunch until eventually it fills in an entire object, like the one you've seen here. And of course, once it's filled in an object, it'll go and verify as far as possible what it can see. Here you can see it testing edges, filling in models, then going around finding another edge that looks particularly as though it would support a hunch, and then filling in another model and so forth until it's found and accounted for all of the objects that seem to be in this particular bin.
But it can only deal with those particular objects?
It can only deal with those particular objects. You'd have to teach it a new object for a new bin.
That looks to be very sophisticated. Is that state-of-the-art?
That's pretty much state-of-the-art in industrial vision these days, yes.
Right. Thank you, Mike. We'll come back to you later.
In summer 1986, Microlive visited a project at Stanford University which was attempting to create what might be called an intelligent robot, a robot which could combine vision and sensation and some kind of understanding of the real world.
Stanford University is one of the world's leading centers for research into robots. Stanford employs Dr. Stefan Michalowski to research into one of the worst problems left behind by the Vietnam War: how to give some freedom back to war veterans who've lost the use of their limbs.
If you want to pick up a flower, it's very easy for you and me to do. And we really have three things going for us. We have a very good manipulator, our arm, with lots of articulations and muscles. We have very good sensation in vision and touch. And most importantly of all, we have this fantastic computer, which is our brain, that allows us to coordinate all the sensations and all the movements. Now, if you want to do the same thing with a robot, then you really have your work cut out. And so what we've done is we've put together this manipulator, and its dexterity is provided by 6 joints, 6 degrees of freedom. They are controlled by a computer on board, and there is a certain amount of sensation in this hand, in this end effector here. Now, the key to success here, really, is to allow the user, the paralyzed user of this device, to look at the situation, to judge what kind of movements have to be executed, and then to tell the robot what the robot should do.
Placing the flower in one corner of a living room creates yet another set of difficulties. Stefan's solution involves a disabled person directing the robot from a computer console.
Define vehicle points.
Stefan can define a path on the computer which the robot will follow.
Mark point.
The computer is programmed by nothing more than movements of the head and spoken commands.
Mark point.
Sensors on either side of the screen detect the position of Stefan's head. After the robot has been told to cross the room, the computer monitors its progress on the screen. The robot has 3 special roller wheels, which are arranged at 60 degrees to each other and so allow the robot to move in any direction. The tricky bit occurs when the robot arrives at the flower. Stefan is now guided by a television camera which looks down the robot's arm.
Upward, upward, forward.
This allows him to maneuver the robot's hand into a position where it can grasp the flower.
Close hand. Upward, 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 forward. Vehicle mode. Backward.
So, after many words have been exchanged between Stefan and the computer, the robot can finally carry the flower across the room. Stefan admits that there is still much work to be done in robotics to imitate the ease with which the human brain can command the human body's movements.
The biggest problem is that commanding a device, or a human for that matter, to execute simple motions on command, which is the way our system works right now, is a fundamentally unnatural way of doing manipulation. When an able-bodied person does manipulation, they do it basically unconsciously. And to have to concentrate and think about each movement in particular, forward, backward, the way the robot works now, it's unnatural, it's frustrating, it takes a long time, and eventually people get discouraged.
Well, it's easy to have a simple programming language and just have single words, do this, do that. But of course, a person having a robot help with a meal, to get in bed, or any of the many things that a person might want a robot to do, wants to speak in a very natural way. And to assume the robot has a background and can follow instructions the way a person does. And it's a very complicated problem to move from the very precise language of programming to the robot understanding and being able to carry out instructions spoken in English.
Upward, upward.
Well, there's nothing so subtle and marvelous as the human vision system or the human auditory system. Just take the vision system. There certainly is not going to be built into a robot in the same amount of space, let us say, the capabilities of the human vision system in any near future. So we must deal with something very much more limited. And it'll be limited for quite some time. Now, it isn't just the the vision system in terms of talking about the eye and how the eye works, it's also the way the information that comes into the eye is cognitively organized in the brain. I mean, that's a very complicated and intricate affair. And how's a robot going to do all that?
Professor Supes there from Stanford University, contemplating the problems of getting robots to understand the world as humans do. Fred talked to Professor Brady about further academic research in that area.
Let's start off with the grippers, the hands. What's new?
Well, in our first video clip, we can see a robot hand that's been developed by Ken Salisbury, first at Stanford University in the United States and subsequently at MIT.
A lot of flexibility there. It's double-jointed, isn't it?
Extraordinary flexibility. The hand was actually designed to be able to grasp an arbitrary object. It doesn't know anything about this can, but to be able to move it in any arbitrary direction and impress an arbitrary force on it. There was no attempt here to mimic human hand design or human hand control.
Is there any point in mimicking a human hand?
Yes, indeed. As the next video clip shows us, if it were not for the example of the dexterity of human hands, we may well have given up the task of trying to build robot hands with similar dexterity years ago. Here we see a system which has got 4 fingers. Each one of those fingers has got 4 different actions or joints, and each of those joints is pulled by 2 tendons, much like in a human hand. So there are 32 actions in all, unlike the 6-motion robot that we saw earlier in the program.
And the motors are remote from the hand themselves?
Yes, indeed. They're down that rather little marionette arrangement that you can see on the right of the picture there.
Why is it twiddling its fingers, Mike?
Well, really it's a demonstration to show just how fast a modern robot dexterous hand can go, because for a long time people suspected that you'd never be able to build very fast hands like human hands. You'd always have to put up with very, very slow and rather cumbersome devices.
Right, and it flicks it away very deftly. Now, those hands had no sensors in them, did they? They were just moving to predetermined locations.
Absolutely, and indeed the attempt to incorporate sensory information, for example, to avoid collisions, as in this clip of film, which again comes from Stanford University in the work of Osama Khatib, illustrates the incorporation of control into planning trajectories for a robot. The kennel is being viewed from a TV camera above. Of course, the system doesn't know anything about Snoopy or kennels or anything. It just sees
recognises an obstacle.
A black
yes.
blob, and if it's there, it'll navigate around it. If it's not, it'll go back to its preset path. Now, this system isn't restricted solely to visual information. Here you see force information being used to control the robot rather than vision.
It's not being pushed up, is it?
It's responding to very delicate forces as delivered through a sponge which is being held by this operator here.
And it's hardly being deformed, that sponge.
It's hardly being deformed. This has got tremendous reactivity to external forces.
What's all this handshaking about?
Well, the basic idea is that much of assembly and much of machining these days consists of, as it were, bringing robots in graceful collisions with the external world, as for example in this scrubbing application, or in here in following a contour. So we want to be able to program forces. Here's a rather different one though, where the work of Jim Trevelyan in Western Australia, where we have a little sensor that appears to be simply flying at about 1/8 of an inch above a human hand that's moving around.
Why would you want to do that?
Well, the secret is in the little end effector there, which looks like a comb. Indeed, it's a cutter. This is a robot for shearing sheep, and what it does is it goes in and it's attempting to cut the wool.
Yeah. Oh, that's a real live sheep, isn't it? I saw it twitch.
It's a real live sheep, all right.
We're not going to see buckets of blood, are we?
I doubt that you'll see buckets of blood. You actually probably can see one slight nick, but you should understand that this system cuts a sheep about 1/100th as often as a professional sheep shearer would.
That's a moving, breathing sheep.
Yeah, the key to doing this problem, in fact, is not only to have this sensor which is gliding over the surface of the sheep cutting, but to have a model, a kind of CAD model, geometric model of the sheep, which is used to plan paths, but where the sensor essentially adjusts its path to glide over the surface of the sheep.
A flexible model.
Indeed, a flexible model.
Now, all those robots we saw, including that one, were routed to the spot. What's happening about robots moving around?
Well, here you see an example of a walking robot, although wheeled and tracked robots have also been built. This is a system that comes from the University of Tokyo. It's the first robot that was unstable in the sense of falling over when you turn the motors off, but can stand upright when you turn the motors on.
Now, hold on, Mike. I've got a son who has a clockwork toy that seems to do exactly what we're seeing here.
Right. Hold on, Fred, you're wrong. The basic idea is that in your child's toy, the center of gravity of the system is deliberately pitched low so that it's stable and it won't fall over. Here, and in particular in this one, which is the marvelous work of Mark Raybert, first of all at Carnegie Mellon and more recently at MIT in America, of a system that's trying to balance. It has a very high center of gravity and stopping this thing falling over. Yes.
I wouldn't have thought that was possible.
Yeah, well, nobody did actually until about 5 years ago, till Raybert showed that you could in fact build a balancing machine.
Why would you want a hopping robot?
Well, the idea of this system is that balance is central to ordinary human or animal motion, such as walking or running. Here you see a two-legged version of the same thing. It's actually two of those one-legged controllers that we saw in the previous video clip. This thing is alternately being a left hopping machine and a right hopping machine, and by switching between those two legs, you can gain the effect of running.
It's detecting a tilt and then it's responding to it either by correcting it or by, in this case, it's building on it.
That's right. Running, in a sense, is controlled prevention of falling over. And it's shifting its center of gravity and adjusting its stride pattern accordingly. And by changing it in various ways, you can increase the speed of the robot. Here it's reaching somewhere between 12 and 20 miles an hour.
Took a tumble there.
Indeed. This is a four-legged robot which is built from the two-legged robot in pretty much the same way as the two-legged robot was built from the one-legged robot. You pair off couples of legs, here the diagonally opposite legs, to provide one of the so-called gaits of the mobile animal. If you choose different pairs, you get trots or bounds or what have you.
Have you taken these movements from nature? It does look as though it's been modelled on a horse galloping or trotting.
Well, actually, engineering and the studies of human and animal motion are informing each other here. We didn't know very much about human and animal motion until we started to build the engineering devices.
I can start to see a use for a four-legged machine because rough terrain would obviously need something that could adapt as it moved.
Indeed. The principal application of these kinds of walking machines is, in fact, to march off the road and into forests for lumbering, particularly in the Soviet Union and Canada.
This research all looks very exciting, but what's next? How do you pull it all together?
Well, what we've seen are a whole series of very exciting devices, but what we really need to do now over the next few decades is to bring the kind of very intelligent controlling software that we get from artificial intelligence and use it to control some of these devices.
But just in case you feel all this is science fiction, take a very quick look at this educational robot with Mac.
Well, if you want to learn about robotics, something much cheaper will do. For £175, you can get a teaching robot like this one. It runs on a single micro, and you can see here one of the devices that tells the micro how far this part of the robot has moved. There are a series of marks on these wheels which reflect infrared light, and a sensor counts them. To tell it what to do, the instructions are written in a simple control language, rather like BASIC.
Well, that's it for this week. Remember that for notes to cover the whole series, send a large stamped addressed envelope to Broadcasting Support Services, that's BSS, PO Box 7, London W3 6XJ. That's BSS, PO Box 7, London W3 6XJ.
And please remember to enclose 75 pence. Bye-bye.
Goodbye.